of the instrument when it comes to taking a measurement either for the ozone or for the UV. And I will just briefly go through that list with you. So you see that for the ozone measurement, we make direct sun measurements with a narrow field of view, while for the UV measurements, you will measure the global irradiance through the Teflon diffuser, looking at the whole upper hemisphere. So you have a field of view of actually 2 pi. While in the ozone measurement, you are using the ground quartz. In the UV measurement, you are using a Teflon diffuser. The ozone measurement is able to choose the neutral density filter attenuation automatically. That's part of the ozone measuring procedure. For the UV measurement, this is not automatic. It's something that you have to set up yourself initially. The measurements are done through all the exit slits nearly simultaneously. Tom mentioned that this morning. While for the UV measurement, you are mainly using slit 1. And at the end of the sun spectrum, you are switching to slit 5 to extend the solar spectrum by about 15 nanometers. And you are switching to slit 5. The measurements are done quasi-simultaneously, while in the UV measurement, they are measured sequentially. So a UV scan will take between 5 and 7 minutes to measure the whole spectrum. That means also that the measurement is really not simultaneous. Every wavelength is measured at a different time. That matters when you have conditions where you have, for example, clouds. So you cannot assume that your solar spectrum is really measured at one instantaneous time and represents one snapshot of the radiation field. You have temperature corrections in the ozone measurement, while in the UV measurements, this is something that has not really been introduced operationally. The measurements of the ozone is relative, so you are making double ratio measurements, while for the UV measurements, you are making an absolute measurement. You are actually getting out, finally, a measurement that should have the units of watt per square meter per nanometer. Finally, the calibration of the ozone measurement is usually done using a travel standard instrument. At the campaign, through collocated measurements, you will obtain a calibration for the ozone, while for the UV measurements, calibrations are done with a reference lamp and not through a comparison with another instrument. So the main characteristics that you would need to characterize or to know when you're taking a UV measurement is, of course, its responsivity, spectrally. You need to know the wavelength of your different measurements. You should have a good knowledge of the spectral resolution. It's helpful to know your angular response of your Teflon diffuser, temperature dependence, linearity. These are the main components, and I will go briefly through some of them. So the most important is, of course, the calibration of your instrument, and that means the sensitivity of your instrument. And when you take a measurement, then initially all you get is a signal, in this case from the sun, that would be in photons for a certain time unit, photons per second. And you convert that to an absolute unit by dividing it with the responsivity of the instrument. So if you know that your instrument is responding to a certain amount of radiation with so many photons, then with that equation you can calculate the absolute irradiance of your measurement for a specific wavelength. Now, how do you get the responsivity? The responsivity you get by measuring a known radiation source, typically a halogen lamp, 1000 watt, 50 watt, whatever you have in your lab that has a certificate that specifies that for the specific wavelength, for the specific geometry and setup, you would get this amount of radiation. And when you make the measurement of this reference lamp, you would then be able to determine your responsivity. And when I plug in this responsivity into my equation above, then here you find out that actually when you are taking a solar measurement, then you are relating directly the lamp irradiance of your certificate to the solar irradiance that you're measuring outside by a simple ratio of the instrument that was once measuring the lamp and that is now measuring the sun. And what this equation implies is that your instrument is actually linear. And it's not obvious that this is the case. As you can see here on this figure, where I plot solar spectra for different conditions, one for high sun, one for low sun. And down here, you see in green actually the irradiance of a standard lamp. And the difference between these is a factor of 10 to a factor 100. So it is not obvious that your instrument is behaving the same way when it is measuring a very weak lamp like that or the very powerful radiation from the sun. That is something that we take for granted, but you will see it's not really the case. You really have also to make sure that your instrument is behaving properly. And Tom mentioned that. Also, the brewer is actually implementing a very nice correction algorithm for linearity using an exponential correction based on a dead time that is individual to every instrument. And when you plug in this typical dead time for an instrument into this equation and you calculate the amount of correction that occurs, then you find out that for roughly 1 million photons per second or 1.5 million photons per second, your correction will be of the order of 5 to 6%, something like that. And this is actually what is implemented into the ozone algorithm. And I would say that this is quite a nice ballpark rule of thumb figure that you can use when you set up a measurement and you don't want to exceed too much in the linearity of your instrument. Then try to stay here within that order of magnitude, 5 to 10% maybe. And that allows you then to finally choose your neutral density filter in your instrument when you are taking a UV scan. You will be at a specific site. It is individual if you are in Finland or if you are somewhere in the tropics or in Tenerife. Then of course you will have different conditions. So your neutral density filter might be chosen differently depending on the amount of radiation that you will have at noon time in June. And this would be one possibility of selecting the right neutral density filter. I put in that figure, that slide, because I don't think it is really obvious to most of us that when your instrument is giving out the counts that you can see from your files or from your measurement, then even though we all know that the brewer is counting photons, when you're actually making your measurement, it returns counts, which is not photons. It's actually 4 photons per 1 count. And when you are taking an integration time and you specify a number of cycles, and it's not really, when you say 4 cycles, it's not really 4 cycles with that integration time, but it's actually 8 cycles. So these are things that you will find in the manual. And when you know about that, then you can transform your counts that you are measuring to photons. Now you wonder why that might be important, because we will calibrate it out anyway. Well, it matters on the one hand for the linearity, because the correction for linearity using the dead time algorithm requires photons. And on the other hand, we also have the possibility of using some nice Poisson statistics. Tom mentioned it also this morning that the brewer is counting photons. It's a random process. You can use Poisson statistics. And the Poisson statistics have this nice feature that when you have been measuring for a certain amount of time and you have been collecting so and so many number of photons, then you can use this number to actually already calculate the variability of your signal. It's just the square root of n. So when you take one single measurement and you know the amount of photons that you have, you can already have a good estimate of the variability of your measurement. You don't need to repeat the measurement 10 times to get statistics. The one single measurement of the number of photons already will give you an indication of the statistics. And you can see down here, it's quite nice because you already will get an idea of the variability of your signal of the data by knowing that when you have 10,000 photons, you will expect something like a 1% uncertainty. To decrease that by a factor of 10 to a tenth of a percent, you will actually need to have 100 times as many photons. You already have to go up to about 1 million photons. So when you're setting up your measurement, when you're, for example, in the laboratory and you're taking a measurement of a lamp, then you can use the measurements of the number of counts and the photons so that you already get an indication if you need to increase your integration time, have some more cycles, or maybe change the geometry if you don't have enough counts or maybe too many counts. I'm moving on to the wavelength scale. How do we know the wavelength scale of our instrument? Well, this is the mechanism that is used in the brewer to move the grating, that is then moving the solar spectrum on the different slits of the instrument that then reach the photomultiplier. And when we are speaking of micrometer steps, then we are actually speaking of this micrometer here that is pushing that rod that is then rotating the grating. And in that whole mechanism, there's really nowhere an information of the wavelength itself. The information of the wavelength we get by making some measurements of particular emission lines, where we know that, for example, a mercury lamp in that region will only have radiation coming out at this one wavelength. So we can measure in that area, and when we find the peak of this emission line, then we know that the rotation of the grating corresponding to a certain position on the micrometer will correspond to that wavelength. In practice, this will look like that. On slit 1, we measure from 1,000 to about 7,000 micrometer steps. We move through step by step, rotating the grating and measuring the output of this mercury lamp. I'm not sure if this is not maybe a combination of mercury and cadmium lamp. And you see that at various positions, you will get these emission lines that you can attribute to these different wavelengths. Then you specify a relationship between the steps and this wavelength, and that is what you get and to obtain a dispersion relation. This dispersion relation typically in a brewer is quadratic. For this example, I've put it here. And you can see that this term, the zero order term, corresponds to the wavelength where the micrometer is at step 0. This here corresponds to a wavelength increment for one step. So maybe you remember this first of my slides showing the schematics of the brewer. I was saying that a micrometer step is 0.007 nanometers. You actually find it from that equation. And then you have a small residual quadratic term. And this equation allows you now to put the wavelength to a specific micrometer position. And this is something that is valid for the UV scans, but it's equally used for defining the ozone position and for calculating the ozone cross-sections and everything. So this type of characterization is used both for the ozone and for the UV characterization. This is a little bit of more detail. You see that actually you have a slit function of your instrument that is not monochromatic as Tom mentioned this morning, otherwise we wouldn't have any signal left. So it has a certain width, and in the brewer there's a specific procedure how you then specify the center of this slit function. You can see that there are some straight lines drawn on this plot. It actually corresponds to a triangle where both sides are at the same slope. So it's an isosceles triangle. It crosses at a certain place, which is then defined as the center of this slit function. You see here there are a few points on each side of the slit function that I use to constrain this triangle. And this is the mechanism by which, from taking these measurements of the various slit functions, you then specify a particular position, and you can then attribute this micrometer position to the wavelength of this line that was measured in this case. Now this is quite critical to know the resolution of your instrument, because your solar spectrum has an incredibly high spectral information, and depending on the resolution of your instrument, you will be measuring slightly different types of spectral information, shown here as an example for two instruments that have 0.5 nanometer, which is typical for a brewer, or 1 nanometer, which you can also find for other instruments. And you can see already here, for a particular part of the solar spectrum, that these two instruments, even though they are measuring the same sun, they will be not giving you the same answer for a particular wavelength. Then you will have this blue curve where you see that this instrument is behaving like a very nice instrument, allowing you to choose only the radiation for this particular area. But then about a factor of 1,000 less, you will see that all the radiation that is coming from the far end of the spectrum will still be able to get all the way through the instrument onto the photomultiplier. And the reason for building the double monochromator was to improve the situation by placing a second monochromator at the exit of this first monochromator to enhance this rejection of unwanted radiation. And what you see here is actually the second monochromator. You see here nicely the first monochromator that is the same for the blue and the green instrument. But while the blue instrument doesn't have a second monochromator to reject this type of radiation, you see here the second monochromator coming in and also removing that part of the radiation. Now this is not only academic, but it's really something that you can see in your instruments when you take measurements. And I've plotted here on the right the comparison between, in this case, the double brewer, this green curve, and another instrument that were both taking the same measurement of the sun at the same time. And you see that all the way down to below 300 nanometers, both instruments are actually agreeing very well. While when you are looking at the same measurement but using a single monochromator, you see that the single monochromator is measuring really enhanced radiation in that area, which is coming from this part of the solar spectrum. I will not go into the details about the angular response, just to mention that this is something that you should take into account when you are analyzing your data, because it can mean that, for example, even though your instrument is very well calibrated and very well characterized, you will still have a deficiency of between 5 and 10% relative to unity. You will have a diurnal variation, and you will not see that on your own. You can only see that when you are comparing your instrument to another instrument that doesn't have the same problem. The temperature correction is also a characteristic of your instrument that you should need to consider. This is an example of a single brewer that I have been using some time ago. And you can see that the temperature dependence of this instrument is not constant over wavelength. So it's slightly changing over wavelength. The overall effect of this particular instrument is about 0.3% per 1 degree change. If that doesn't sound like a lot, then think that these instruments are not temperature stabilized, and depending on where you are, you could easily have 20 degree changes during a day. And if you have a 20 degree change, then that would amount already to about 6% change just due to temperature. A further problem that was found out quite recently, not even 10 years ago, was that your entrance optic from the global UV port, it is made out of Teflon, has a really annoying feature around 19 degrees, 19, 20 degrees, where the transmission is changing quite abruptly by 2 to 3%. And this is something that it's very difficult to take that into account in any post-processing. It's much, much easier if you could avoid it by being either above or below the line. Now this can be done on some instruments where you can maybe stabilize the detector. In the case of the brewer, this is something that you might really need to think of how to take that into account. For example, if you are able to heat the diffuser material by being above, or you make sure that you are always below in wintertime. That brings me to the end of this presentation. I would like to go through with you a very simple procedure of how you would go from a raw measurement of a solar spectrum to the final product, which is a calibrated irradiance spectrum. So we start off with a raw spectrum that is measured in counts. I've drawn here an example for a single brewer, so it extends all the way up to 325 nanometers. I've drawn it here in a linear scale. I will be jumping between linear and logarithmic. That's why I have added this information that you can see the changes. The first step in the calibration will be to remove the dark signal. So we will, before starting a solar measurement, you will have closed all the light throughput to the photomultiplier, and you will be measuring just the output of the photomultiplier to when no photons are coming onto the instrument. It's actually a very small value. You will still remove it, and you see here on this graph that you don't even really see a big difference here on this logarithmic scale. The next step, we are still in the count room. In the case of a single brewer, the procedure that is applied in the brewer operational software is that you can remove the stray light with a very easy procedure. The instrument always starts measuring at 290 nanometers. Some are starting at 286 nanometers. But this is a region where usually you will have no radiation from the sun. So if there is a signal, then in the case of a single brewer, you attribute all of that to stray light. So you take the average over these 2 nanometers and you subtract it from the whole spectrum. When you do that, then you can see here that you move from this black and green curve to this red curve, which looks more realistic. We finally come to photons. We convert to photons per second. We go from the counts, we multiply by 4 because of the pre-scale on the photomultiplier. We divide it by the integration time, and we end up with photons per second. We correct for linearity using the exponential equation. And you can see here there is already here a change of about 3 to 4%, going from this black to this blue curve. And the last step is to apply the sensitivity. And you can see that now finally the solar spectrum is raising all the way up to 325. Before, you remember, it was going down funnily. That was not part of the solar spectrum, it was part of the instrument, in this case, the nickel sulfate filter. So this is the end of the standard brewer operational software, and I guess this is what you will be doing in the practical session afterwards. The more advanced analysis might also take into account temperature corrections, wavelength shifts, spike corrections for those that have been looking at data from some older brewers, cosine corrections. There are many additional activities and characterizations that can be applied to the Brewer UV spectrum. Okay, that finishes my first part of the presentation. Any questions? For example, but this is also not operational. But in my case, I always calibrate my instrument without any neutral density filter. And then I know the transmission of my neutral density filter because I have measured it with other methods. And then in my analysis, I will take the sensitivity I will take my measurement that has been done with whatever neutral density filter I needed, and then in addition I will apply the known transmission of this neutral density filter, and this allows me to have a lamp calibration without neutral density filter to have high counts. Well, you know, here, this figure over here, it is made with this subtraction of the stray light the way I just explained it by taking away these 2 nanometers. And even with this method, you can see that you're still having a lot of stray light. So if you don't apply any stray light correction, I don't even want to know how that would look like. And this here, this 10, 15%, around 300 nanometers, will not affect your dose that much. But a stray light correction has already been implemented on that graph. And it just shows you that when I did the measurement, it was not really that consistent. So I could either take that measurement and I would end up with something around here, or here, and I would have a correction of about 0.35 or 0.25. So that gives you, let's say, the uncertainty of my correction that I can apply. Which would mean that if we take a value and we multiply it by 10, either I make a correction of 2.5% or 3.5%. It's not that critical. Well, we were discussing that at one of the cost meetings, and one problem might be that this here was measured with the 50-watt lamps, and this one was measured with the 1,000-watt lamps. And the 50-watt lamp system sits right on top of the diffuser, which might mean that it's heating up the Teflon of your entrance optic, which might affect the temperature coefficient. It's certainly a different geometry, either having a lamp somehow 50 centimeters away, radiating everywhere, or having this really closed enclosure that is really heating up your instrument. It might be an explanation why this is inconsistent.